Right, good.
Oh, yeah, you're good.
So, are you good with the recording and stuff?
Yeah, it's all good.
Okay, perfect. So I also have like an hour and 30 minutes full breakdown of the architecture that I already edited and recorded. I'll send you the link if you want to. In it, I go through this the architecture, the code, and how to set it up, and all this stuff. So before I start, just to present myself, I'm Yacine. I was at McGill in actually computational neuroscience way back in 2021, I think. I was doing my bachelor here. I did a master at the IPN, and then I did a PhD. Anyone here in neuroscience? No? So what's your background here?
There's some comp sci, there's some psychology, there's some cognitive science, some electrical computer engineering.
So a bit of everything.
Yeah.
Cool. And your interest is mainly on AI and how to leverage it and stuff. That's good. Yeah, my background is in computational neuroscience. I've done a whole bunch of research. I did a whole lot of computer science stuff. I was actually tutoring at the Trottier for a long while. I almost lived there. What happened was that in neuro, if you're doing like a study with like the brain and like in my case it was EEG signal, you have to have some ways of like analyzing it. And AI is often a tool that you're going to use to do all sorts of things, right? So I was using models to understand what features were important and be able to kind of go from there. So yeah, that's a bit about me, and then I dropped out. So I published a whole bunch of papers. Then I dropped out, and I created a company in the supply chain domain. So long story short, was with a bunch of friends, and then it worked out, and that's the stuff. So that's kind of about me. I have a background in like practical AI stuff, and on the research side also. So first off, this is Continuous Thought Machine. I really like this article. I also talked with the author of the paper, Luke. You should check out his other stuff. These guys are actively like improving over the architecture. Anyone read the paper? You guys read the paper? Perfect. How did you find it, generally?
I actually I don't have a huge background in linear algebra, so I ended up reading the technical.
The blog, yes.
Blog thing instead. Yeah.
Okay, cool. So put you on the spot. So anyone read the full 40 pages? Okay. So how did you find the article in general?
I liked it for sure. It was really interesting. They're constantly motivating the reason for the architecture. How although right now it's not frontier technology, it is like way closer to interpretability, and that there's huge strides to be made there. So I found it very interesting, and I could definitely see the reason why we want this.
Yeah. So same thought here. And generally speaking, when you see, like no disrespect for anyone here in computer science, but usually when you see like some AI paper that has some brain related stuff, it's very superficial. In this case, it is not superficial at all. Actually, the guys, I don't even know if I can say that, but the others are currently in Stanford in a kind of neuroscience institute to present the stuff to people that are doing studies neuroscience. So like there is something here that is very interesting, both from a neuroscientific perspective and from an AI perspective. On the AI front, anybody here read the paper Attention is on Me? Mostly classic. If you look carefully, one of the authors of that paper is on there, right? And it's like the supervisor. The stuff that like I'm gonna show you, it's mostly it's mostly toy stuff, right? Like there's no benchmark that we're like exploding or anything like that. It's mostly like a feasibility study about the core internal of the model having nice properties, right? And these properties then could be studied in different ways, and then we can augment that with like language and all sorts of stuff, right? But this is how you should look at the paper, because if you look at it, you see ImageNet, right? You see like Cypher, you see a bunch of maze puzzle thing that you can solve deterministically, right? Which is not that impressive in and of itself, but the fact that this thing works and how the latent representation is done is actually pretty interesting. It's very close to how the brain operates. But that's the stuff. What I'm going to do today, how much time do I have? I have an hour, right?
Yeah, but if you want to go overboard,
How much time do you guys have? That's the more important question. I'm gonna aim for an hour, and then if you guys want to stick around for like some other stuff, because there's like it's 44 pages of very interesting experiment. Each of them are super interesting. I'm gonna show you three, the two main one, and then one that like I just like, and I'm gonna walk you through the architecture. Just with the architecture, I think we're gonna be good. We're gonna do that in the first 8 minutes, and after that, I'm gonna show you stuff. So. This is this, right? This is the continuous solution. So we're looking at this. There's a few things that you like that is apparent here. And three main things, right? First thing is that there's a model inside the model, right? And two times. There's another model here. This is an MLP. You can actually change it for other stuff. And this one is a unit, but you can also just have an MLP. There's also another model that is hidden, which is over here, the data. And this is whatever backbone you're using for your specific task. So if you're doing image, it's going to be a ResNet here. If like you want to use something else for another modality, you just swap the backbone over there to put it into the embedding. You see also attention, right? There's an attention like mechanism in here. And there's a lot of arrows in this, right? So the flow of the information is actually how to say recurrent, right? But everybody knows like the RNNs, LSTM, that sort of stuff. Kind of the same vibe, but if you're looking at it, we're not recurring through data. We're recurring through time, right? There's another paper that came out recently, actually from someone in Montreal, Alexia. For the TRM, so the tiny reasoning model. It's a very cool architecture. It's a small paper. It's like 12 pages or something like that. But also in this paper, you see like some reasoning. Some recurrence, not on the data points, but on the full thing through time, right? So that's one of the most important things to take out of this whole mess. Is that the data here is just one of the first input, right? But then after that, it's the model that is kind of thinking through the system, right? A bit like chain of thought with LLMs. Same idea, except a bit more elegant because we're not like spewing out a bunch of tokens and feeding them back autoregressively. We are staying in latent space all the time, right? So that's the stuff. And then this is the neural things, right? So this is where we're gonna see like the actual, what's that? We're gonna see the, let's go. Okay, I can click on this, wow. Okay. I'm not gonna, should I just, not click my, okay, so I'm gonna move a bit away from this bad boy over here. So yeah, the neuroscience stuff is in the synchronization thing, and there's a whole bit of them everywhere. So the three things that you have to keep in mind is that it's recurring in the latent space. Latent representation is actually something neuroscience that we take from neuroscience, which is the synchronization between different neurons. And there's a whole bunch of different models that are mushed into it, right? We're going to go slowly. We're going to go from 1 to 10, right, so that you understand all the architecture. But if at no point does it make sense, right? Literally, if you nowhere where you're gonna start, it makes sense. It makes sense in the way that the system kind of works. A bit like the brain, you cannot just take one neuron and say like this is where it starts. It actually is always ongoing, right? If you have any question, as I'm writing here, don't hesitate. Okay, so we start here, right? So this is a synapse model, and like I said, this thing is a unit, right? So it look actually a unit look like this, right? So pretty standard structure where you have like the encoder decoder part, and then like goes smaller in the middle, and that's kind of the shape of it. There's nothing like crazy here. You can also replace it by NLP. It doesn't matter too much. The input is what matters. So here you have the ZT, which is the post activations, right? So this is going to get confusing because you have pre-activation, you have post-activation, you have the output, you have the synchronization, right? You have the actual output, and then you have the latent representation that goes through attention, that is the output. So none of this is supposed to make sense at this point. So this is the post-activation that gets fed from the output of the previous stick. So you already have the time domain that is entering. So if you're thinking about like what's happening at time 0, there is some learnable weights, some learnable initialization that you can put there, right? So assume that we are at like 10 step already in the system, right? The start doesn't matter. So the input is the post-activation. So when you went through like the second system that we're gonna see, and the output completely of the whole system. So both of them get tagged together, right? And they get like concatenated. So you see here, this is the output, this is like the post-activation, and it goes into this the synaptic model, which is just a unit. So the synapse model is how you kind of mix the output of all of the neurons together. So this is where they mix one time, right? There's another place where they mix, but it's their latent representation that is mixed up. So they mix here, and then you're going to create pre-activation, right? And the pre-activation is like it's the output of one neuron with respect to the other neurons, right? For one time step. And what we're going to have now is that we're going to start to have these time step saved across time. So you have actually now a time series that is saved for each of the neuron, right? Literally like a neuron that you were recording in the brain. Right? So you save that, and like you may ask what happened if the tick is too long. This is a moving window, so you kind of forget about the past, right? So there's a kind of moving window happening here, and then you go into the neuron level model. So this time series is the input for the MLP that you're going to see here, that will then create the post-activation. So if you were to imagine what a neuron is in this specific article, and they actively mention it, it's an MLP, which is composed of artificial neurons. This is a bit confusing, right? And why they're doing this is because, like, MLP is more closer to an actual biological neuron than an artificial neuron is. Because the human brain neurons can learn XOR, right? They have like some sort of like learning mechanism of some sort. Like a single neuron in an artificial neural network is nothing, right? It's like a line with a nonlinearity, right? So this is how they model an actual neuron, and this neuron is they have this pre-activation history. So what happened through time, and then it goes through the neuron as the input, and it is able to do a little point that will be called the post-activation.
Are all of the pre-activations going through the same weights in the
No.
MLP? No.
Each of the neurons, literally the neuron in this bigger system, is its own model. So it has its own learnable set of weight. So the neuron is learning something, right, with respect to all the connection with the other neuron, what happened with their time series. So that's kind of how it goes, their time series and the output previously, right? So this is also important. So all of these signals get mixed up over here, And then you get a post-activation, which is also just a little point that you put. So you have to keep in mind the concept of time. This is why it's a bit wonky at the beginning, because like there's no time series, right? So after some tick, then you have this time series that kind of just goes. So you have this time series, and then it's called post-activation. And what happened with the post-activation? It goes back into the input, right? So technically here, like you could stop your understanding, and it's going to be like kind of okay, right? You can assume that output magically appear, and then we're good, right? So this is like a motion that is going tick by tick. But if you look just at the upper level, there's no data here at all. There's absolutely no data that is coming in. The data in the continuous state machine is kind of secondary. It's not the most important thing. It's really the representation that is happening. A bit like in the TRM also, right? You see the puzzle, you take the input once, and then you always keep a handle on the output, but then you have this later representation that you're working with, right? So you should think about it a bit in this. Actually, it's a good thing to think about. So you have your X, right, which is your input, and it can be a maze. You can have this, and then you're supposed to go like over here, right? And actually, if it's the input, you have none of this. You don't have a path, right? And then you have like in your specific case, you have a Y when you're training this stuff. You know, like from here to here, the optimal path is this, right? And then you have the latent. We can call it Z. Right? I think in this case, Z will be the post-activation, but in our case, it's going to be also the output. Like this is like kind of similar here. And this is your scratch pad, right? You can think about it like, okay, this is this now. And then you can actually do stuff like this in the scratch pad. It doesn't matter. So if you were to interpret this, it will be hard. In the TRM, it's the same thing, right? You have X, Y, and then this Z, which is latent. Like, could you have another latent also, so multiple scratch pad? Technically, yes, but it doesn't help. So you have this. What's interesting here is that in the second lower part, we're going to see this latent representation is encoded in the interaction between all of the different neurons post-activation, right? So we're here. There's a history that gets like saved in this buffer, right? And in this history is like the same thing as the pre-activation history that we just saw, right? But now it's like the post-activation that went through this learnable neuron kind of weight, okay? And then what we're doing is we're looking at how these neurons are synchronizing together. So what it actually looked like, actually this is one of the coolest. So like this is just a U-map of all of the activation together, right? But you get this, like the red is like it's less synchronized to like whatever this neighbor or whatever it is, and the blue is like it's more synchronized. And this is across, let's say, 100 tick for an image. So for like an ImageNet, like a object detection type of stuff, right? That's this thing, right? It's actively trying to like refine its Y, right? And then try to figure out like the right answer. But it's through the dynamic of each of the neurons interacting together. They're not all interacting together. We're gonna see in a few seconds. There's actually a subset, but that's the general idea. So this is what's happening here in the synchronization, and it's being encoded in this latent space. There's a direct transformation, a direct calculation that you can have about synchronization. You can do a whole bunch of them. And what's funny is that in my studies with consciousness, I was like developing like a kind of graph representation of the brain, and we had like 128 EEG electrode, and we were looking at, there was two metrics that I was looking at: the phase lag index, so the amount of lag between, let's say, one electrode to another electrode. They give you some information about like what's being sent out, roughly speaking, functionally to another region. You can also use like the amplitude envelope correlation, which is looking at like the correlation of the amplitude. It's kind of a similar type of idea where you have like one neuron talking to the other neuron. In this specific case, however, there's no concept of geometry, right? The neurons are not like, there's not like, if you look at this thing, this is not like a lobe or anything, right? It doesn't mean anything. It's like a flat grid. But that's it. So this is yes idea. There's no concept also for the neuroscience nerd. Inhibition, right? There's no inhibition here. In the brain, inhibition is kind of useful in order to kind of create these more like defined mode of the brain. Here it's just like excitatory completely, right? But that's pretty cool. So then you get like this grid, but you're just selecting a subset of the grid, and then you're creating your latent representation. So your latent representation is like this subset of neurons connecting together. You take like some subset of it, and this is how you encoded that stuff. So this latent representation is yours. Yes.
In that video you showed us, does the X and Y like position mean anything?
It's a UMAP. So it doesn't really mean anything. It's like how you can think about it as like maybe how closely, more tightly connected they are in the sense of like how they're firing. But this is not angelic sphere. I don't think they explained that much. It's a UMAP. It's a lower dimensional representation of the latent representation.
Okay, and then the colors we saw was how closely correlated they are to each other?
So it's if they were red, is at this point in time they were not synchronized much with whatever they were synchronized with, and if it was at the blue, I think they were more synchronized. So it's like you can see these waves of synchronization, which is fucking cool. Like I don't know. I'm used to look at brain stuff. Like they actually look like on top of it, they put it into a brain shape, but I don't know if they did it on purpose or something. This like sold it for me. As soon as I saw it, I was like, this is my favorite architecture now. Okay.
I'm
so,
sorry.
You go ahead.
Could you explain once again how they do the subset selection?
The subset selection
Yeah.
randomly.
Oh, okay.
It's completely random. So they did a whole bunch of them. The only reason why they're selecting a subset is just that it's computationally too expensive
Okay.
for them to select everything and look at everything and have a big latent representation. And I think the actual answer was that when it's too much, it might not have worked. There's a lot of moving part in this thing, right? The fact that this stuff is working is a miracle. So you have to put it into perspective of like the initial transformer architecture, right? If you think about it now versus what we know, it looks like square wheels, right? It doesn't make any sense, right? But now we know and we refine it and stuff. Kind of the same idea. So you have your latent representation, and then at any point in time, you're outputting two things, right? There's linear transformation that happens here in order for you to output something. So in this case, let's say it's like, I don't know, the full grid to do the path of the maze, or it could be like the actual label, this is a cat, or whatever it is. And then there's like this kind of softmax thing that you can do in order to select all of them, right? Or, well actually not or, and you shove this into an attention mechanism with the data, right? So, where was the data? The data is here, right? There's like I shouldn't just touch this. So the data comes here to like one of the backbone, and then the embedding of the backbone. So like some of the weights, the last layer, like encode the data in some way, and they get mixed together in the attention mechanism, right? And this attention mechanism, the output of it, is the output that you shove for the next tick. So that was one tick, right? This goes on for like 50 or like 100 tick. And there's a very interesting dynamic that happened. Like honestly, if you don't have the time to look at the whole thing, like this blog post is pretty solid. You can see here in this little image how the neuron dynamic specialized after training. So you take this whole soup of model and then like synchronization and you train it on like, I don't know, ImageNet, and you get these neurons like specializing. You see this one, like it will be activated in a specific pattern in general, right? You see this one is like a bit less like specialized. You see the average is a bit more messy. If you were to look at the LSTM in comparison, the LSTM will be a bit more random. There's no specialization in like in the neuron here, but here it does seem to specialize. So this is this, and if you look here, this was this. I think I looked at this one is good, right? So this is a dog, right? You can all agree that it's a dog. And there's a whole bunch of like different sort of dot in ImageNet 1K, right? And what you're seeing here is like, this is the average attention, right? The model has like all of these cool properties, which is like a lot of interpretability that you can get out of the box, right? So you can see with the attention mechanism, what's the global attention looking at, right? And you can actually trace it because you have the time dimension, right? So this is like across time what's happening. At the beginning it sucks. After some time, you see when it's green, it has the right label, right? And the little line here at the axis is certainty. So it's 1 minus normalized entropy, right? And it's able to know how certain it is about its label. If you're interested in some of the architecture, there's a whole line of model that have this kind of adaptive computation time characteristic, which is you can adapt the compute to like figure out if you should spend more compute in order to get a better answer, right? The LLMs are doing kind of this when you're doing like scaling at the inference time, right? TRM is doing the same thing. You can actually like train it just for 16 tick, the TRM, and then during inference you can scale it to 400 and the performance will just increase, right? Because it's actually refining the latent again and again and again. And this is what's happening. At the beginning the latent is all messed up and the label is garbage. And then as it goes, the latent becomes like crisper and crisper to the point here that like it doesn't change. The latent like stay fairly similar and the output stay the same because it's super duper certain that this thing is true, right? So that's what's happening. And then like because there's an attention mechanism, there's actually multiple heads. And this is better. You should not have just one head, you should have multiple ones. And then each of the heads are looking at the data in a different way, right? So they're kind of encoding some sort of like feature detector at the higher level, a higher dimensional space. You see like this one is like looking at the border for some reason. This one is looking at, it seems like the blacker stuff, right? So the darker thing. Some are more local. This one doesn't move at all, right? It might be dead. Also, it might be not useful at all. And others are like more global. They just go and trace the whole thing. And this happens not just for like image recognition. It also happens for like this is a parity type of task. It's an easy task in computer science, right? So you have this grid, and then you have to kind of calculate the parity of it. So there's like a literal algorithm that you have to operate, and it's like in a snake like fashion. And then you see like the output being refined over time, and you see like here what each of the heads are looking at, right? Some of the heads are just specialized in white. Some of the heads are specialized, I think, in black. This one at the top is just specialized in black, right? What does it do? I have no clue, but it's doing well, right? After some times, it does get the answer. And then you have the same sort of human, right? But you see how, I don't know, it's beautiful. Like it's doing something, right? It's doing something, and there's an actual algorithm that it's learning. And depending on the number of tick that you give it, right, it will learn different algorithms also. So this is it. So this is the structure. Any questions so far? We're at the high levels. But any questions? Go ahead.
To learn like different tasks, what part do you have to swap out?
Yeah, you swap out this one, right? Just swap out the backbone that is doing the encoding for the embedding. Yeah, that's pretty much it. And then some like, if you're trying to max out the amount of performance, sometimes it's better to have an MLP here, right? Sometimes it's better to have like something else. Here, the ResNet that you can put for the image stuff, like you can alter a whole bunch of things. But this is already trained, and you just like use the embedding for it. Yeah, so that's kind of stuff. Like most of it is pretty similar, but you can just swap out some of the backbone, and you should be right. But in all of their experiment, they train one CTM for a specific task. So it's not like a general thing. Same thing with the TRM. It's like one TRM for one specific task. But you can think about ways of doing this in a more like kind of general pre-training type of fashion.
In the same way that like you would say LLMs are maybe generalizable. Like if you encoded text in there, you could maybe do
something like this, right? So if you're able to find, because anyone here like learn about like segment anything model? Have you seen it? Right. So it's like the similar idea than like LLM for text, but for image segmentation, right? So they found a way to kind of define the task so that it can just run. It can just do the thing, right? So that's what makes the LLM so scalable, the pre-training, because the task is simple. It's like just next token prediction in some way. So if you can define this, if you can find a way for this architecture to kind of just go and do just one thing that is super easy and super simple to figure out, you can get some generative setup out of it. Right now, it's a puzzle solver. Right? Like there's nothing crazy about it. And if you just look at it from this lens, it's kind of a bit boring. But the important part is it's working. They're good.
Two questions. One, I was wondering how the synchronization improves performance. And I was wondering if you can talk about how you would work with text, possibly as like an LLM.
Yes.
For like LLM type purposes.
So the synchronization with text will not change. I think it will be the same thing. But this is just like each. I think I actually can pull out the paper. I have the notes here. So this is for neural pairing and neural synchronization is right. So so you have like you can use just like the dot product here, and you get your ST here, right? So this stuff, you could do it simply like that. But what they're doing on top is that they have a subsampling approach. So they're not taking all of the pairing, but the synchronization is as simple as this. You can have something a bit more intricate if you want to, but right now they're having like a very, very simple baseline like that.
Why does this improve like performance on like an intuitive level? Because they like are more aware of what the other neurons are doing, I suppose.
So from a conceptual level, what you're encoding is like we're at a very high level at this point, right? So you have the data that goes through an attention mechanism, right? So there's like some attention element on the output, and then all of this soup goes into a synapse model that is looking at like all of the previous latent information that you had and the output, and mixing them together in the unit, right? Kind of encoding them kind of together. So like whatever signal you had before for a neuron kind of get shifted in some way from the previous one, right? And then over here, for each of the neuron, they kind of learn to specialize in some way on some particularity of the data, right? Based on like the mixed signal. And then this whole thing is a time series, so it also look at the past stuff that it has before, and they get shoved into the synchronization. So this is what you're actually looking at. You're looking at like, if we trace it all back, you're looking at the modified interaction with the rest of the network and the output, right? With respect to what you're specializing in as a neuron. And then you're comparing this for each of the neuron together. But you're taking a subset of it, right? But let's say you don't take a subset of it. You compare this with every other thing, and this is your latent. So this is very, very hard to kind of understand like what it means. But that's also what's happening in the brain. Like it's very hard to just pick a neuron and say like, yeah, this one is doing that stuff. Like, yeah, it's doing that stuff, but it's also like long-term potentiated by stuff that happened in like the hundreds of neurons that is touching it in different ways, right? And then this whole mass in time is encoding like the element, and you can disrupt them, you can do all sorts of things, but that's kind of what we are. So the latent representation here is like it's really powerful in some way, and it's closer to what it's very interpretable. So let's see this one, right? Like look at how it's looking at this stuff. Like for the general average out thing, right? It's not looking at the tent, the backline. It's looking at the dog, and it's looking like at the various part of the dog, the face and stuff, right? So you can already get that with like a CNN, and you can look at like what it's looking at. But in this case, you have it in time. So you have the dynamic, as if somebody was actually looking at the stuff. And they added some more neuroscience scientific stuff. They added like a foveated vision to some of the neurons for the image task, and you literally see it move through, let's say, a tiger or whatever, and you can look at like where it's concentrating, like the spot where it has the highest accuracy of the highest resolution of the vision. So it's very, very brain inspired, but not in a dumb way. I would say, like, if you ever read the HRM, like, no disrespect for the HRM author, I think it's a great paper, but like it was inspired by the brain in a very naive way. In this case, it's like engineered to really look like what the vision part of the brain is actually doing. And you can also see it in how it's solving the maze, right? So the maze task, actually, there's an interactive version of it, which is pretty cool, right? So you have the maze, and I never know, the start is the red, and then the end is the green, right? And then you can just like run it, and then it will go and do it. So this is a train one, and you can move, let's say, where it starts, and you can let it run. This one, it's struggling a bit, right? If you can move it here, maybe it's going to find the path. And in this specific case, I just gave it, I think it has like 50 ticks. So sometimes it cannot go and execute a task because it doesn't have enough tick to move, right, and to find the path. This, you can see it in all of the different experiments they're doing. But what's interesting is that once it's trained and you're looking at the attention mechanism, it has an algorithm that it learned in order to move to the position that it wants, right? So if you look at the maze section of the paper, you're going to see at some point that it's kind of reaching out through its attention mechanism to kind of look a bit ahead, and you can define and deduct a bit the algorithm that it's using. Any other question here for the architecture? That's that. I don't think that's right.
So you were showing earlier like a video with like the different changing of like how each node were each neuron and each were synchronized. But then there's like a tick here that like it looks like to me that it synchronizes at every tick. But like, so how do each neuron get synchronized?
Yeah. So like if you look at the synchronization, it's a dot product, right, between like two post activation. Right? So this is like the number that you get out of the S thing, and this number is happening across all of the different neurons. So this is like your measure of synchronization. We're just taking a subset of it, right? We're not taking the whole thing. We're taking just a subset. So sometimes like there's not that much activation that is going on in both of them, and it's only excitatory. So if both of them are very excited across this history, like the number will be big, and if like some of them is not excited, there will be lower like measure of activation, synchronization. Okay, somebody had another question. Good. Okay. So actually, like there's a whole bunch of different models in it. In this big model, there's a whole bunch of them. So it's kind of an ensemble of a soup of different models. So here you have the ResNet that is actually, yes, it goes in here, right? You don't see it in this, but like it's over there. You have the Synapse model, which is a UNet. It's like over here. This is like just this very simple NLP. This is a very simple NLP, right? There's nothing complicated over there. So there's 1, 2, 3, and then there's the attention heads over here that is just calculating like the simple attention stuff. If we look actually at the code, right? It's a bit different how they show you can see the code, and you actually have the code in the repository. It's very well written, right? So very simple. It's like MNIST. You can check out the video that I've done. I broke down like every little pieces of it, but it's not inherently complicated what's happening, right? So if we break it down here, you have like the backbone, so the feature encoder, and here just a bunch of definition we're doing, right? So I'm going to show you like the whole architecture into the code. So you have a bunch of definition, you have the backbone that you're going to use here, you have the TV projector and the Q projector, right? The TV projector, you're going to just use it for the data coming in once, and the Q projector, you're going to use it like a thing. You use your Q and your TV there, and then this attention out is the output that goes into the synapse model, which is a UNet, right? It goes here. You get your pre-activation. This pre-activation gets shoved into a history, so you're keeping everything, and it's a first in, first out. So after some time, you have a bunch of the window that just remove a part of it. That's it. If you look at it holistically, right? This whole thing, there's a whole bunch of moving parts and decision you have to take. So for instance, the window. Like what window size you should use? 50, like 100, 3. And if you use it here, should you use the same like over there, right? The backbone, how big this thing should be, think about it more like as a very artisanal type of first sketch of what this latent reasoning type of stuff that is brain inspired should look like. Does you have a question?
Yeah. It's just I'm a very complete AI beginner.
Yes.
So when you said that the model uses time as another dimension, in the code, is it implemented through the for loop? And it's
The for loop, exactly.
Yeah, and
Right.
it's like every iteration of the for loop is just a new time step.
And you time step, exactly.
Yeah.
So like when you have an RNN or like these other like recursing model, you have like the stuff going like this, right? And then you have, let's say, like this block of the RNN. Actually, you never seen it like this. You've seen it like unroll through time, right? So you unroll it through time like this, and this is like x0, this is x1, this is x2, type of thing. And you can have like multiple row of it, and then just like fed like this one after the other. We don't like to train this because it takes like a bunch of time, and then like the first input get kind of diluted over time, right? So this is why kind of transformer win, because transformer has like all the x0 to xn against like all the x0 here to xn, and then you look at the attention, right? But in our case, like you have a bit of all of this. You have the bit of attention that is there as in a transformer. You get this idea of recurrence, but not in x, right? You have it in time. So at each time step, you actually what you have is the full grid, and at no point you forget where you started. At every point you have your actual x that gets fed, like the whole thing in here through the attention mechanism. So this thing, right? So you never forget where you started. And the same thing with the TRM. It's the exact same thing, and it gets fed back again like this, again like this. So you're starting to seeing a pattern of two things emerging, right? So there's this latent reasoning through time that is happening, that is not present really in its natural form in the transformer architecture, decoder only architecture like an LLM. The chain of thought is kind of doing this, right? It's kind of like feeding itself back autoregressively again and again and again, but not during training at inference. So you get the same idea, but directly in the weights. So it's hard to interpret what the Z is doing, but you can see it, and this model actually is more interpretable. So yeah, you have a whole bunch of these models, and this is the time steps that are happening, and then you're kind of overwriting on the Z, but taking into consideration every other point in the Z, the latent space that happened in the past, and you're just moving this way. Then you have the pre-activation history, we talked about that, the FIFO, and then this is the neural level model. So it's a models, so there's a whole bunch of models for each of the neuron, and you shove the pre-activation history, and then for each of the model, it has their own little history that goes into it, and then you get this output. Like, could they do without this part and just use the pre-activation? My guess is it started there and then like it was still too raw, right? So the learnable weight per neurons is helping a bit, like taking the compass into account and simplifying a bit, like the output. Yeah, you add this into the post-activation history, and then this is where we're computing like the synchronization. So we're computing the synchronization on like the action. So this is what goes into the attention, and then the output. But it doesn't matter. Like it's kind of the same idea. And then you output the history. You add this to the output history, and then the output history goes back into the model again and again and again. You can technically do adaptive compute time here by stopping after some time, right? The TRM is doing this a bit with like the Q head and stuff, but in their case, they just went through the whole So that's pretty much that for this section. This is the neural synchronization element, and you see it's nothing complicated. It looked complicated because it did something here interesting, which is the decay, the importance of the past in trying to figure out like the synchronization. So like if they synchronized highly, like at 50 time steps ago, right? Should the number still be big, right? Is it still relevant that the number is big? Theoretically speaking, not really, right? But actually, it didn't matter, right? And like in the paper, they actually mention it. They mention it here, right? For full disclosure, we found that the CTM never leveraged this for the for ImageNet and for the maze thing, which is the two main thing. The decay element of the synchronization is not that useful, right? Is it because it's not a good idea, or because some other part need to be refined, or the tasks are too easy and stuff? Hard to say. But if you just take like the dot, it's good enough. Like it's not a problem. And then you just subsample from that, and you should be good to go. So this whole part is doing this. It's just like an exponential decay factor, and it's learnable, which is cool. And this part is the neuron level, and the neuron level is just like, see here, we have weight bias. It's a two-layer perceptron. There's nothing crazy. That's the whole architecture.
I have a question.
Yes.
As far as I know, usually in latent embeddings, we assume that, like, we intuitively think that one element of the vector has a meaning in like a dimension. Like, for example, it can be like if you're like seeing images, it can be like, or the first element encodes height, or like,
Yes.
Yeah, right? But in this one, you subsample your latent vector randomly. So the inputs or like their meaning can change with each iteration, right? Like latent embedding elements doesn't necessarily have a meaning like that we usually think they have.
Yeah, exactly. I think in this specific case, they do. I think the random sampling is at the beginning,
Oh, okay.
and then it stays. If I remember correctly, I might be wrong here. But this is also another question here. I was a bit skeptical here. This part is arbitrary, might be a target for refinement. Usually, your neurons that fire together end up wiring together, so over time, some connection should drop. Blah, 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 blah. But also here, I think they're going to refine this stuff.
Okay.
But if you think about it from the get-go, at the beginning, it doesn't matter. Like each neuron is like they have no place in space, right? So each neuron is arbitrary. Actually, if you define that, like, okay, these should connect together, these should connect together, fine. You create a graph, and then you're like training this graph, and then this graph will learn to work together. And like this neuron is connected to 5, this one is connected to whatever. So that's kind of how it goes. If it changed every time at every tick, then it's a bit weird, right?
Okay, yeah.
This part I would not understand how it would everywhere. Yeah. Okay, so that's for the architecture. Any question about the architecture before we move on quickly on the 2 pages?
On the neuron level MLP, do we find it like intuitive to go like higher in dimension on the hidden layers, or just the same?
I think they tried it out. They tried a whole bunch of stuff. Like so, like it's 58 pages. Like these guys have been like, they've tried everything that worked. Every idea I think was in there, but like MLP alone is fine enough, right? Even here in the signups, you don't have to actually do a unit. In some cases, MLP also is good, but you have to understand what they're doing. They're doing ImageNet and Cypher, like a maze, right? So it's not too complicated that much. So there's a lot of part for refinement, which is exciting because this thing is, I don't know, like there's a lot of things that you can actually test yourself and then just ablate some part and then just test out. The code is all open source. You can actually see everything. Any other question? Yeah, go ahead.
Is there a biological motivation for like subsample? Or oh yeah, you explained it.
Well, like a neuron, like in the brain, the neurons have a specific connection pattern, right? Like if they fire together, generally they will wire together. That's kind of the idea. But there's also the inhibitory neuron, which is fired to another neuron. Like they create circuitry that is like behaving in a certain way. Some neurons are always inhibitory to one neuron, that when like it doesn't get inhibited, it just fire like crazy, right? And then there's feedback loop on the same neuron sometimes to then excite it back to make it stop, right? So there's all these intricate kind of pattern of structure. We're not there, right? There's only purely in like excitatory neuron architecture, and we're not doing like some crazy like actual like brain stuff. We're doing image recognition, right? So it's a maze solver here, and then we have like a ImageNet type of thing. But it's the other bits that are interesting. It's these ideas that we have that is interesting. So for me, the synchronization part, I also found it pretty arbitrary. I think in another version of it, they're going to do some more tests on this, and it will maybe look a bit more intricate. Actually, the end one of the other, and like, hey, try inhibition, and he's like, huh, I'm not sure if he's going to try it, but maybe. Anything else before we go and look at some of the results? So some of the results. I'm just going to go here to see. So the first one is ImageNet, and ImageNet 1K. So there's 1,000 class, right? And just with this graph, you see something very interesting, right? So this is like through the internal tick, the percentage of data that they got positive or negative, right? So we got correct or it didn't got correct, right? But if you look at like one tick, they put a threshold of like 0.5 here, right? And over there they put a certainty threshold of 0.8, and the certainty is like 1 minus normalized entropy. Like there's only 40% of the data they have an actual label. So the model literally learned to shut up, which is super important in some specific cases, right? If you try to wrangle an LLM to shut up, it's very difficult. You really have to do a lot of tricks to just tell it like, if you don't know, you don't say anything, right? But in this specific model, you have it kind of out of the box. It has a measure of its own certainty of the output based on its latent and its training itself. And the certainty actually do make sense. So if you take a very hard ImageNet and you, there's one that's even high, like I don't know, like what I've done wrong, trick. And I'm pretty sure all of you would have done it wrong. It's here or like that. I don't remember. It's a fucked up fence, right? Really messed up fence. I think it's a worm fence. That's what they said in the paper. No way for me to kind of know. And then you see it like struggling as it goes through this like weird imagery, right? I don't think they've seen a lot of these fences in the training data. So it was literally not certain a lot during and he got it right, but like it was not certain a lot. So as you add some tick, it's the same model, right? as you add some tick, you see the performance kind of like skyrocket here. At some point, it kind of stay constant with a certain threshold of 0.5. So it got a lot of the stuff negative. Well, just a portion of it that is negative, a good portion of it that is positive. You can reduce the negative by just increasing the certainty threshold. So it has less negative. It will also have less answers, right? Only if you give it 50 tick will it start to always output something. So you get this ACT kind of adaptive compute time. That's not ACT here. You get like you get both. You get the ACT because you can decide if your certainty is low, right? Let's say you have like very low certainty at the tick 1. You can say like, I'm gonna do another step, see what's up. Is my certainty increasing or not? I'm gonna do another step, and then you keep doing steps until like, yeah, we're like, I'm fairly certain here, we're out of the threshold, or I'm out of tick, and then I just call it a day. And you also have the fact that you can just shut up. So you can just say like, after 50 tick, I have no clue. I have no clue what you're showing.
So the more ticks you're in, that your activation is going to change less by each tick, right?
It's a bit more complicated than that, but like at each tick, you're just changing the latent.
Okay, yeah.
So you're modifying the latent until this latent, you look at it and then you're like, I'm fairly certain.
Okay.
Like this is this label. So it's this with this that's gonna give you your certainty measure, right? And then you're like, yeah, fairly certain. This is the thing. That's what you get here. And then they did a whole bunch of stuff here. Is not too important. So they tried a whole bunch of things. Like there's a lot of engineering that went into this. Really cool that like this lab is actually going to this direction and it's like trying like this weird architecture. So the other thing that you have is like if you look at this and you're like, yeah, I'm gonna go 50 ticks all the time, right? Not all of the data is the same, right? Some stuff are easier. So for instance, so if I give you like a whole pile of image and like this is the test, guys. Like we need to do the test and like get a good grade, and then like you have like as much time as you want, right? But there's a timeline of like I don't know, 10 hours to go through the whole pile. Like there's the animal pile, so the dogs and the cats, and then I give it this to you and you look at it. Are you gonna spend as much time on the dogs and cat than like on the fucked up fences? Like no, right? You're gonna just look at the cat, and you're just gonna blaze through these in one tick. But the rest, you're gonna spend more time and you keep maybe for the end and like spend more time like figuring this out. This is kind of what we see, right? So you have the count over 80% certainty across the internal tick. So there's much more of them that have like a high certainty at the lower amount of tick, and then you kind of have this burnout chart of like the rest that is left at the end is harder and harder. So you can do the adaptive compute on the data that you have and decide to spend more time on some of the element versus others, and you can do that also at training, right? So during training, you don't have to spend like as much compute throughout the training. So maybe at the beginning, like cats, you have no clue what the cat is, and the dogs, you've never seen a dog and a cat. After some time, you kind of figure it out. So these you skip fast, and then you spend more compute on the part that matters. So there's a whole line of research that is in this direction. You get this out of the box, yeah, it's just this is the text. Look at this. Yeah, I give you this. No way you're gonna tell me this is like a worm snake fence. What is that? Look like the trenches or something. I have no clue. I was looking at this. I had zero clue. And you see like the model is struggling right at the start here. I spike. Think he got it. He didn't get it. And I think he got it right here, but I didn't forget about it and said something else. But after sometimes he got it like he got the right label, and this thing is kind of in upward trend. Yes.
I didn't quite understand how certainty is calculated.
Yeah. So the certainty is calculated over here. You have the cross entropy, and then a corresponding certainty measure CT, we computed T as simply as 1 minus the normalized entropy. So you have like your cross entropy, which is like YT, Y true, and then at compute time you can have like a measure of that, which is the normalized entropy. There's a specific like measure of entropy that you can use.
So normalized entropy does not require the true.
No, you don't.
true Y.
You don't.
Okay.
You don't.
So it's like kind of how much is changing, like it's changing less per iteration.
Yeah.
Okay.
So if you look at the loss also, like the loss is very like intricate. So during training, you have the point of minimal loss that you're using and the point of maximum certainty that it's being used. Right? So I think we did it this particular way to be able to kind of have a more like an intricate behavior during test time. But there's also this element of computer planning. There's a lot of things in this paper actually. It will take more than an hour to discuss. Then you have the maze stuff, right? And the maze stuff also super interesting. But this is literally like a maze solver. Like, there's nothing inherently that complicated with the maze solver. It's just that like it's learning the algorithm in order to do it itself. So like you will see a lot of mazes, so 39 by 39, and at some point you will learn the algorithm. And the interesting thing here is they compare it as an LSTM, right? Kind of doesn't matter because the LSTM always sucks. But the CTM was better than the LSTM. The more training iteration, the more ticks you give it, the better it is. The interesting bit is here. There's an emergent behavior where the CTM attend along the path beyond its training step. So if you give it 50 steps, it needs 100 in order to get there. It will still attend to the rest of the path. So then if you give it 100, it can actually go there, right? And in a whole lot of ablation, and not ablation, but like trying to generalize it, you can actually like give it a much bigger maze, right? And if the thing is solvable in like, I don't know, 100 steps and stuff, even though it was trained with 39 by 39, it can generalize to 99 by 99 mazes. It breaks down when like you hit a certain point, because like never, in the training with 39 by 39, it never went past 400 root length, but it's still able to do some of them, right? So it actually is kind of learning an algorithm out of the whole situation, which is fairly crazy. It's great.
I was a bit confused. Is it like, does it get a pixel grid of the maze, or like how is it?
You get the
interacting?
whole maze, and then like it's actually encoding it like as a vector, and then you just like this is the thing that you shove in the backbone.
So the maze is encoded as a vector, and then it's like steps. How does that work? Like when it makes predictions of like where to go?
How you make prediction is predict the whole grid with the route given.
Okay.
So it's like you can see it as like, am I here or not, right? And am I using this as a route or not, right? And then like you have to actually do a route that is valid, and then like at each point you give the whole grid. So at every tick you're just outputting grid. So this is why the latent can be messed up. It doesn't matter, right? It's not the thing that you output, but the actual output that goes through like this linear edge has to have like a specific format.
So the output might be like ones and zeros of like where,
Stuff like that. I think
something
it's,
like that.
it's a bit different than that, but and its direction. Don't remember exactly. Yeah, constrain the output space. We record a solution in the form of a fixed size array, length 100 and 24, containing one of 5 movement type, left, right, up, down, or weights per step in each of the element of the grid. Right? This is again type of solution, blah, blah, blah. So that's kind of what they're doing. Right? So like it's a harder task than in some of the other model where you have like positional embedding to be able to understand like where everything is in relation to everything else. So they wanted to build its own inner world representation out of stuff. But it's outputting the grid again in any solution like last or long. The TRM is doing the same thing also. Okay, this is the stuff, and that's pretty much it. So the maze is pretty cool. And there's a last one that I want to show, but I've got, I think we're done. Yes, go ahead.
Can we go back to the certainty histogram?
This one? There you go.
No, I don't think so. It's in the actual paper on page like halfway through.
Here?
The one we're showing like as yes, that one.
Yes.
Why as number of ticks increases you have fewer counts?
So this is the count. This is the V. The V we show a histogram data point exceeding a certainty of 80% for each atomic tick, colored in class indices and whatnot. So like this is the count of data point that at time 0, sorry, at the first tick, there's a certainty of over 80%, right? So there's some subset that it knows straight up that is the thing.
Okay.
At 80% certainty. Some, they need 2, right? And then the bulk of it, if you see here, is like around here. It's pretty good, right? And then as you go, there's some element that you need more and more ticks in order to have a certainty above 80%. So this one you have to sit with a cup of coffee for like an hour, right? In order to understand it. It took me like 2, so you should be good with that.
So it's removed from, like, it doesn't make predictions on it once it's like done its prediction?
So like this is just like quantifying the data points, right? And like trying to figure out like, are they all super hard and they require all like 50 ticks, or are they all super easy? Actually, there's a distribution of them. Some of them, like actually the bulk of them are fairly simple, right? And then as you go, some of them require more and more tick, and like these last one, like the worm fence for sure is here.
Okay, so this is out of like all the like
All of the
possible
data.
data points and you're just adding them.
And this is 80% certainty,
Sure.
right? So if you had 50% certainty, it will be different kind of structure, but it's connected to this one, this plot that you see here. So like if like some data point that like here will for sure kind of always be able to output like the element. So this slice over here is what is being used to say the stuff over there. Right? Okay, go ahead.
So it's the same here.
Here.
So for the dark blue class, with more iteration into more ticks, it gets more uncertain about that class.
It's like this is I think that for the class thing, like some of the element is are in a have more of the specific task, the specific class, but like the dark blue here, some of them are very simple, and some of them are harder and harder. That's kind of how you should interpret it. So it's not the same data point, right? So it's like, let's say this one over here meets one data point of this specific class. This one is super duper hard, right? And another one that of the class is like super easy. So kind of the stuff with like the baby poodle and the muffin, right? One of the image of the poodle is looking like really like a muffin. So do you guys understand what I'm saying? Did you see the image? Thanks. This is the muffin poodle. Okay. The last thing I wanted to show you is it's like deep in the paper. I think that there's 6 people that actually looked at it over there. This is my favorite one. So the task is it's MNIST but with a question, right? So you have a bunch of MNIST image that you're going to give, and then you have a question which is this thing. It's like a mathematical kind of question, right? And you're going to give this stuff across tick. So you're not going to give it all at once, right? So you see at the beginning of this video, you see it gives 6, 5, 6, 5, whatever, and then it gives encode like the transformation that you should be doing across in order to the transformation that you should be doing to these numbers, right? And the position that you set in order to like have the answer to this question, to this mathematical question. So the answer of this is 9, right? But throughout, you can look at the attention, you can look at what the whole network is doing, and you can look at the end, how certain it is for what the number should be, right? So like look at it closely. Okay, you see like at the end 9 is like it knows it's 9. At the beginning it's not moving much, right? But while it's doing the stuff, you see there's these blips, right? These blips correspond to the middle solution of this question. So it's actually trying to answer the stuff, and it's gonna output the last thing when it received the equal sign, which is like now answer the full thing, and then it's gonna like output the 9. But throughout the stuff, it's actually like it built an algorithm to like look back in its internal representation, like where the 5 is, where the 6 is, and then we do this transformation, and then this should be the output at this point in time, and then we go. Okay, now we're done. Then I output the full thing, and I output the 9. And this is interesting for many reasons, because like you can actually I have to dig deeper to find out here. You can actually increase the number of operations and it generalizes. So like it learned to, with 4 digits, to save the 4 digit into its latent space, right? And then just like manipulate them over time. And so even though it was trained for 4 operations, it can generalize to like 10. So the algorithm is like something that is ongoing. It doesn't generalize with another digit because it doesn't have enough space in its learning setup to save this somewhere. So it saves just 4 digits, right, in the latent representation somehow, right, in the like synchronization between all the neurons. So this is super interesting because like an LSTM breakdown, it's not able to do that when you have like more ticks. It struggles a bit, but this architecture is able to kind of go and have this algorithm and run with it. Both of them like break down at the number of digits that is increasing. So this is pretty cool. So like you can see that as it goes, like here it says 2, right? It's not the wrong answer, but it's the right answer at this point in time. And you see here, there's this 1 because it's actually the right answer for the whole thing, but it's also the right answer at this point in time, and it just goes. Did a whole bunch of stuff with like reinforcement learning and stuff. The gist of it is that it's a very intricate kind of architecture, still very like artisanal a bit, right? There's a lot of improvement that can be done in many directions. But the cool thing is that it's using all the interesting bits of all of what we learned. There's attention mechanism over here. There's a unit here. There's like some stuff with neuroscience. We have like the MLP to like do the things. We have like the temporal element of it. We have like the recurrence through like this latent kind of scratchpad type of stuff, like the LLM with the chain of thought. So all of this is kind of put it into this kind of brain-inspired setup. And in each of the little experiment it did, like it looks a bit human how it's learning the internal algorithm to solve the problem. So it's really like problem solver type of stuff. I will not be surprised if they tried their hand on the RKGI soon, right? So this benchmark, because the puzzle solver like this are doing great. So the TRM is one of them that is also doing great. Yeah, so that's it. So any question, you can come see me. But I hope that this was useful. You can also watch like the full video that I've done on it.